Okay, here we are back for the second video lecture of the course. As announced, this is going to be a refresher about, basically a lot of things that you should already know, but maybe, don't have super clear in your head anymore, or could use maybe a little bit of going over again, just to make it sharp and clear again in your mind. So basically, what I'm doing in this lecture is I'm going to go over the most fundamental statistical prior knowledge that you should already have. It's going to be a little bit intense, of course, because basically what I'm doing here is I'm compressing an entire course worth of statistics lessons into one single lecture. But I hope it will help you to remember what you're supposed to know and maybe find out what where your prior knowledge maybe is lacking a little bit. So basically, I want to talk to you about three basic concepts from statistics: central tendency, dispersion, and it's going to take up most of the lecture, inference, the challenge of saying something about the population based on just a sample. Right, so let's just dive straight into it. So central tendency, what does that mean? When we talk about central tendency, what we mean is that we somehow want to describe the central value of the distribution of a variable. So we want to describe, so it's descriptive. We want to do this through a number. So we're going to calculate some statistics, so a descriptive statistic that is going to describe the central value of the distribution of a variable. Well, what is a value? A variable? A variable is some characteristic that we have measured for our cases, for our observations. And it's called a variable because it can vary. It can take different values for different observations, for different cases. So, for instance, the variable might be how much people like statistics, liking statistics. Let's assume uh, I'm interested in analyzing how much my students like statistics, then I might want to measure that variable. And then, of course, some students are going to absolutely love statistics. Maybe even most students are going to absolutely love and adore statistics, but maybe some not so much. And some might actually actively hate statistics. So different students will take different values on the variable liking statistics. So in other words, we get differences, so we can look at the distribution of all these different values. And probably what we'll find is that, the very extreme values are not going to be that common. So the number of students that absolutely hate statistics is probably going to be not super large. And the students that think that statistics is the best thing to have ever happened to them in their life is probably not super large. So somewhere in the middle, probably you will see most of the observations. So the idea of a central value is the idea that somewhere there is this kind of central value that indicates, roughly speaking, what is the most likely, where most of the values are concentrated in our distribution. Um, so there's different ways of trying to pinpoint that statistic to give it a number. And the three that you know about is taking the mean, and more specifically the arithmetic mean, or taking the median, or taking the mode. Especially the mean is something we'll talk about quite extensively now, because it's going to be very, very fundamental to the rest of the course that you really understand what a mean is, and how to interpret the mean, how to calculate the mean. So the mean is one way of getting that central value. Median and mode, not going to be so relevant for this course, but you have heard about them before. So the mode is just the most common value, the most often observed value, and the median is basically just if you would line up all the values from small to large and you would chop your data down the middle, then that number would be the median, where you can chop it down the middle, basically. So, but let's talk about the mean. I drew this graph here to give you some kind of stylized, abstract representation of what we are talking about when we're talking about the mean. So we have here an x-axis running from left to right, And that, for whatever variable we're interested in, would indicate the values of that variable, where here would be the low values and here would be the high values. So from left to right, we get lower to higher values. And the shape of this curve indicates how many observations we have for all of those different values. So here you see the typical bell-shaped curve, where you see that the extreme values are not so common, and the values in between, so more towards the middle of the scale, are more common. So the idea of the mean is that, well, we have this hypothetical distribution of a variable, and the mean is supposed to indicate the top of that distribution, the central value. In other words, basically the most likely value that you can find in your data. Yeah, so the mean is a measure of the central tendency that's supposed to reflect the top of this distribution, the most likely value. So that is what the mean is trying to represent, the central tendency, the central value of our distribution. Now, we of course have to somehow find the value for the mean, assign a value to that statistic. And that means we have to use our individual observations and do some calculations on them to get our mean value. Now, yes, probably you are familiar with formulas from your previous statistics courses. You probably hate them and fear them. And that's understandable because it is a type of language, but it's like a foreign language. It's not a language that you grew up speaking. It's a language that you have to learn as an adult, and that can make it a little bit daunting. And it's also a language that isn't very closely related to our everyday language. It's very, very formal and abstract. But it is important that you do get confronted with these formulas, because ultimately they will help you. They will help you understand exactly what you need to do, and they will also help you to understand what is exactly happening when you do that, and what the consequence of that might be if you do any kind of mathematical or statistical activity. So they are really, really helpful ultimately. But of course, yeah, you need to know how to read them. So in this course, I'm going to try to, as much as possible, stick to conventions when I write these formulas, because these different letters that you see here, these weird letters and the letters that you know, they are basically arbitrary. We could put in any type of letter or other kind of symbol in that formula to symbolize whatever we want it to mean. But it is, of course, nice if everybody uses as much as possible the same symbol, so we have an idea what we are talking about. So there is some of these conventions that are being used as to how to use these formulas, how to indicate different things in these formulas. One of those conventions, for instance, is to make a distinction between, does the formula refer to something that is about the population, or is it about does it refer to something that is about the sample? And that if it refers to the population, that we then use Greek letters, and if it refers to the sample, that we then use Roman letters. So this is just to help with the interpretation of the formula so that we know what we talk about. So in this case, we are using a Greek letter to indicate the value for the mean. And again, this is a convention. Conventionally, the Greek letter mu is used to indicate the mean. So this letter here that looks like a U, it's actually a mu, the Greek letter mu. And this is supposed to indicate the mean value. Now let me just check really, really quickly if my recording is running correctly, and it is. Okay, so no worries there. So let's go on. So Greek letter mu indicates the mean value, and this is just by convention. And then after the equal sign, we are told how to calculate that mean value. And then again, as you look at the top of this fraction that we have here, you will see another Greek letter, because we also tend to use Greek letters if we want to indicate mathematical operations. So in this case, the mathematical operation that we want to indicate is adding things up. So plus, plus, plus. And in this case, again, there is a conventional letter that is used. It is the capital letter sigma, which looks like this kind of weird, like an E, but not really, thing over here. That's a capital letter, like a letter sigma. And you probably know it as the summation sign, because that's what it's usually used for, to indicate that we have to sum things together. And after the letter sigma after this summation sign, usually we get some kind of indication as to how and what to add up. So in this case, you see at the lower half here, we have the little letter I, and at the top half, we have the big letter N. Well, the big letter N in this case refers to the size of the population. So if our population would be, let's say, 16 million people, then the value for N would be 16 million. So big letter N stands for population size. The little I is the so-called index letter, which refers to the values of the individual cases. And so if you put this little I letter of the summation sign, what you're really saying then here is then sum up for each individual case I until you have added up for all the cases N in your population. That's how you can read that. Yeah, so that's what the summation sign is telling you. And of course, you also need to know what you need to add up. So we now know that we need to add up for each individual case in our population and for all the cases in our population. And after that summation sign and the indication of how to do that, you will find what you need to add up. In this case, it tells you xi. So again, capital letter X and then this little letter I, where in this case, X stands for our variable. So if we have a variable and we don't want to use the full name of the variable, or we want just to talk about an abstract hypothetical variable that doesn't have a name, we usually use the letter X. Yeah, so in this case, X, just the normal letter X, stands for a variable, which of course can take different values for different cases. And to indicate this, we again add this little index I, which stands for our individual cases. So how to read the top half of this formula is add together for each individual case I until you have added together for all the cases in the population the value of our variable X as it is observed for each case I in our population, and divide it again by N, the size of our population. So that's the mathematical formula for the mean. The formula looks daunting, but probably all of you know how to calculate the mean without seeing that formula. It's just add up all the individual observations and divide by, in this case, the population size. We can, of course, also do this for the sample. Because it's a sample, we want to use a Roman letter to indicate the mean value. So in this case, again, I'm following the convention here to use X bar. Yeah, so X with this bar on top, which means the mean value of our variable X. And then if you look at the formula for the mean value for the sample mean, it is basically exactly identical to the formula for the population mean. The only thing that is different is that we now will use a small letter n instead of a capital letter N. And this is just again to distinguish between population and sample. So for population, we try to use the large letter N. For sample, we use the small letter, the lowercase n, just to try to distinguish between sample and population so we don't get mixed up. Like I said, I'll try to stick to these conventions as much as possible just because that's going to be easier and clearer for you. But I also have to warn you, I might sometimes not follow the conventions. And the reason for that is because these conventions aren't exactly set in stone. So different people, different books, different scientists will use sometimes a little bit deviating conventions. And sometimes will also not be entirely consistent. So if you're in doubt, use the Zoom sessions to just ask me about that. But I'll try to keep it as consistent as possible, so you know what we are talking about. Yeah. So these are the formulas. This is very abstract. Now let's apply it, which is probably basically going to be also what we're going to do in the rest of the course. We're going to have a little bit of abstract theory, and then we are going to apply. So don't panic when you see stuff come by that's a little bit daunting the first time you see it, because probably we'll go to an example and then will become a little bit clearer, and then you will have an assignment to work on, and that will make it even clearer still. And then if you have any kind of questions, you know how to ask them. We are there for you in that case. Okay, so let's have a concrete example. It's a hypothetical example. Let's say I have an interest in analyzing exam grades for the course PSRM2, and I have taken a random sample of 5 students from that course. So we have a sample size, in this case, it's a sample of 5. So we could say for each student we have the little letter I to indicate that this is that different students get different numbers indicating which one they are, which case in our data they are. So the I stands for index. Yeah, so the first student gets the number 1 for the I, the second student gets the number 2, the third student the number 3, and so on and so forth. And this is just to allow us to say, well, this is the case we are talking about when we talk about a specific case, this little I, this little index that we add to our variables. Yeah, so 5 students, and I've observed the grades. So hypothetically, let's say our first student scored an 8 on the exam. So the student did really well, probably loved statistics, got a good grade. So the grade X, so the grade is our variable now, but if we just want to refer to that variable in the abstract, we use the letter X with the little index I to indicate that it can take different values for different students in this case. So X, little letter I equals 1. So the grade X for the first student is in this case 8. That student has got the grade 8 for the exam. Let's say the second student didn't do so well, got a 4, so failed the exam. Can of course happen. Let's hope not for you. The grade for X equals Xi equals 2. So the grade for the second student is 4. And then so on and so forth. So let's say the third student scored a 6, the fourth student did really bad, scored a 2, and the fifth student did, pretty okay, 7. So we have 5 students, each one of them has a grade. Now, if I want to calculate the mean value, how do I do that? Well, we have a formula. Well, I put down a question mark here, and I would recommend to you that whenever you see a question mark or something that still needs to be filled in, pause the video and do that for yourself. Try to think about, what would be the number or whatever else there should be instead of the question mark there. Just to keep yourself awake, because otherwise, if you don't keep yourself awake and engaged, these are going to be very, very tough lectures to get through, probably because, hey, there are probably funner things to hear about for you than this stuff. I love talking about it, but I can imagine it's not the same for you on the other end. Yeah, so think about this for pause the video and then go on if you think you have the answer or if you can't figure it out. So in this case, I want to calculate a sample mean. So what do? Well, I just run through the formula that we just saw. What do I need to do in the formula? Add together for each case I until we have reached the sample size. So for each case until we have added together all cases, the value of the variable X for that case, and divide by the sample size. So in this case, we say, 8 plus 4 plus 6 plus 2 plus 7, that gives us 27, and we divide by the sample size. The sample size is 5 because we have 5 students, so we get 27 divided by 5, which works out to 5.4. Cool, great. Not super terribly difficult yet, but good to go over it again, step by step. Okay, one step further, deviation scores. It can be useful and will be useful to not just look at the values that different cases get for their observations, but also look at how far removed those values are from the overall mean value within our sample or our population. And that is what the deviation score measures. So the deviation score tells you what is the difference between the observed value for each case and the mean value. Again, here, trying to stick as much to conventions as possible, I'm using the small letter X with the little I to indicate the deviation score for each, in this case, student, so for each case I. And again, we get a formula how to calculate that deviation score, and it's a really simple formula. It just tells you, take the mean value on your variable X and subtract from that the observed value for that specific case. So how far removed is the value on X for that case from the mean value? You can just do that by subtracting, so you get the difference. So, pause for yourself. What would be the deviation score for student 1? Great. Very, very good of you. 8 minus 5.4 equals 2.6, right? The student scored an 8. The average we know is 5.4. So 8 minus 5.4 gives us a deviation score of 2.6. So this tells us how far removed this particular student is from the mean. And in this case, this student is 2.6 points in grade above the mean. The second student, yeah, again, pause. Great. Yes, this student indeed gets a negative deviation score because this student scored a 4 on the exam. That's lower than the average, than the mean value of 5.4. So for this student, we get negative 1.4, so minus 1.4, because this student scored 1.4 points below the average on the exam. Can do this for the third student. Yes, indeed, it is 0.6. This student scored a 6, so that's 0.6 points higher than the average of 5.4. We can do this for the very sad student 4, who scored a 2 on the exam, so that student has a deviation score of minus 3.4. And we could do this for the fifth student, and we get a deviation score of 1.6, because 7 minus 5.4 is 1.6. Cool. Nothing super difficult yet. Now I'll highlight maybe one thing that you know, but maybe forgot, but that's going to be important. And that has to do with what is the sum of these deviation scores. So, do you know the answer? What is the sum of these deviation scores? If you're now reaching for your calculator or start to write down these numbers to calculate this manually or do this in your head, that's completely fine, but you don't need to, because that number can only take one value by definition, and it has to be the value 0. So if we calculate the mean value and then we look at all the individual deviations, scores relative to that mean value, then if we add up all those deviation scores, the result will always, by definition, be 0, because that is actually mathematically how the mean is defined. So we have this nice simple formula. We could substitute this for a much more complicated formula that will show you this. I'm not going to. You can just take my word for it. But that's basically what the arithmetic mean is. It is that value that if you take the deviation scores relative to that value and add them all together, you get the value 0. So for any other value than 5.4, we would have gotten some kind of sum of deviation scores, some value that's not 0. But for 5.4, the actual mean, by definition, we always get the value 0. Yeah, which we'll see later in the course has some nice properties. But it has also one difficulty, because, well, if we want to look at how far all the students are removed overall from the mean, so taking all the students together, it would be good to somehow have a number that expresses how large these deviation scores are. And apparently we can't just take the sum, because it always winds up at 0. And the reason it winds up at 0 is because the mean value is that value where the positive and the negative deviation scores perfectly cancel each other out. Yeah, that's exactly why the mean is right at the center of that distribution. So yeah, it would be nice if somehow we could get a number that tries to quantify these deviation scores, the sum of those deviation scores, that isn't 0. And of course, there is a trick to do that, and it's a trick that's very often used in mathematics and in statistics. Whenever you're in a situation where the sum of something is going to be 0 because the positives and the negatives cancel out perfectly, the way to solve that, or one way to solve that, is get rid of the negatives through a mathematical transformation. And the most often one used in these situations is taking the square. So basically taking your values to the power of 2, or in other words, multiplying them with themselves. So we can also calculate the squared deviation scores, and they will always be positive. So there's always going to be a positive, because, well, positive times positive is positive, but negative times negative is also positive. So you always get a positive number for the squared deviation score, and that means the sum will not, by definition, be 0. Okay, so what is the deviation score for the first student? Well, the squared deviation score, well, the deviation score was 2.6. So the squared deviation score, 2.6 to the power of 2, is the same thing as 2.6 times 2.6, which equals 6.76. If you don't trust me, get out your calculator. If you ever spot me making a mistake, I promise you, if you tell me and you are right, I will get you some kind of present or cookie, at least when campus is open again. So 6.76 for the squared deviation score for the first student. For the second student, well, that student had a negative deviation score, but that student will have a positive squared deviation score because negative times negative is positive. So in this case, minus 1.4 times minus 1.4 equals 1.96. For the third student, 0.6 times 0.6 equals 0.36. For the fourth student, minus 3.4 times minus 3.4 equals 11.56. And for the fifth student, 1.6 times 1.6 equals 2.56. And now we can calculate a sum that's not 0, that's actually a positive number. In this case, the sum is 23.2. So the sum of all these squared deviation scores is 23.2. Great, at least now we have some kind of number that tells us something about how big the deviations are across all our observations relative to the sample mean, whether they are super close to the sample mean or maybe a little bit more far removed from the sample mean. Now, I'm going to point out another thing here that's related to the observation that the sum of deviation scores from the mean is always 0. And that is that because the sum of deviation scores from the mean is always 0, that also implies that the sum of squared deviation scores from our mean is the smallest possible sum we can get. So in other words, the mean value is that value for which, if we would calculate deviation scores, by definition we get the value 0. And because that's true, it's also true that the mean value is that value for which the sum of squared deviation scores is the smallest possible number it can be. So for any other number for these observations than 4.5, if you would have calculated deviation scores and then taken the square of those deviation scores and then taken the sum, that sum would have been a larger number than 23.2. Yeah, so this is only for the actual mean, the arithmetic mean, 5.4, that we can get this small of a number. And for any other value that we would have hypothetically used instead of the mean and calculate deviation scores, the number would have been larger. And I'm telling you this because it's going to come back later in the course. It might be good also to at least give you a little bit, let's say, a teaser as to why it's going to come back. And that is, with this knowledge, we could say, instead of using this formula to calculate the mean, we could use a different way of calculating the mean or finding the value for the mean. And that would be, if we wouldn't know this formula, but we would be able to calculate the sum of squared deviation scores, we could just do that for different hypothetical values of the mean. And just as long as, until we find that hypothetical value that gives us the smallest sum of squared deviation scores. So that seems like a very cumbersome way of doing that if we just have this simple formula. But it would get us ultimately the same result. And there are actually mathematical ways of doing that. Yeah, so that would be a different way of finding the value for the mean. Thankfully, we have the simple formula, but this would also be possible to find the mean by basically finding the minimum value for the sum of squared deviation scores. Cool. Okay, that's enough intellectual complexity just about the mean. Let's get on to the next topic, dispersion. So we talked about the mean as a measure for central tendency. What is dispersion? It is also a descriptive statistic, so it tries to describe something about our variable. And in this case, it is trying to describe the variability of that variable. So how much do the different individual observations differ from each other overall? How much variation is there in our data? Yeah, so if I ask 10 students how much they like statistics and everybody says 10, I love it, then I have no variation whatsoever. But it also might be the case that every one of them gives me a totally different value. So one is 2, one says 2, one says 4, one says 6, one says 8, one says 10. Yeah, then we get a lot more variability in our data. So dispersion tries to assign a number to that variability. And there are 4 of them that you are familiar with: variance, standard deviation, range, and interquartile range. Where variance and standard deviation is going to be really important for the rest of this course. Range is just simply what's the difference between the highest and the lowest observed value to indicate, well, what is the overall maximum difference between high and low that you find in your data. Interquartile range roughly what does it mean? If we would line up all the observations from small to large, and we would chop the data into up where it's 25%, so a quarter of the data, and 70% or 75%, so 3/4 of the data, then the interquartile range indicates what would be the value that indicates those two breaking up points of the data. Yeah, again, range and interquartile range, I assume you know, but it's not going to be super important for the rest of the course. Variance and standard deviation is going to be super important, really, really important. So, variance and variance. Yes, we can do this, of course, for the population, or we can do this for the sample. So we can look at a population variance, or we can look at a sample variance. Again, we want to distinguish between the two, so we again use Greek letters if we talk about the population variance, and we use Roman letters if we talk about the sample variance. And in this case, we use the Greek letter sigma lowercase, so not uppercase like the summation sign, but lowercase. This little thing that looks like an O with a little bit of a hat or hair in the wind on it. That's lowercase sigma. And we are going to use sigma to the power of 2, or as it's commonly referred to, sigma squared, to indicate that we talk about the population variance. Where that 2 comes from will become obvious in about 3 minutes. We'll use the letter S for a sample standard deviation, the Roman letter S, and that's at least convenient because S, standard deviation, that makes sense. But again, with the to the power of 2, so S squared, to indicate that we talk about the sample variance. So we have a formula, again, that tells us exactly how to calculate this population variance. And what is in that formula? Summation sign again, add together all the individual cases until you have added up all the cases in the population. And what do we need to add up? Well, xi minus mu to the power of 2, where I minus mu is just the deviation score. And taking that to the power of 2 is the squared deviation score. And then we divide that by the population size. Makes sense, right? We saw that the deviation scores tell you something about how far removed the individual observations are from the mean. So if you want to express variability, dispersion, that's a good point to start. We know that we can't just add them up because that always gives us the result of 0. So that's not super helpful, but we know that we can get around that by first squaring them. So calculating the squared deviation scores, and then if we want to have the average squared deviation score, we just divide it by the size of our population. So the variance can be interpreted as the average squared deviation score. In other words, the average squared distance to the average. Or average and mean, you can use it interchangeably, the mean squared distance to the mean, which tells us something about how much variability, how much variation there is in our data. So this is how to calculate it for the population. The formula to calculate it for the sample is almost exactly identical. Again, here, instead of uppercase n, we use lowercase n to indicate that we're talking about the sample size rather than the population size. We use x bar instead of mu to indicate that we're talking about the sample mean rather than the population mean. But other than that, it is almost identical with one little exception. If you want to calculate the sample variance, you have to divide by n minus 1. always. The -1 has to do with the concept of degrees of freedom. It has to do with how much unique information you can draw for a given set of finite observations. And I don't really expect you to really have a deep understanding of why that is. You don't necessarily need to. Previous courses probably didn't explain it super in depth. I'm also going to spare you the details to the extent that I can, to the extent that it's not relevant for you. But intuitively, you can think of it this way. If I look at a variance based on a sample, then what I actually do is I limit the amount of observations that can vary by limiting it to a sample. And that means that that sample is going to show a little bit less variability than you actually want it to show if it's supposed to reflect the right variance. So to compensate for that, we divide by a number that is a little bit smaller, so we get a little bit of a larger value for the sample variance to kind of blow it up again to the right size. Mathematically, it makes sense. It's correct to do this with -1, but I really don't expect you or even particularly want you to have to worry about why that makes sense. But just think of it as, well, if we don't do that, the sample variance would be a little bit too small. So we want to blow it up a bit. And by having this number be smaller, we're dividing by smaller numbers, so the outcome of that is going to be a little bit larger. Of course, with large samples, it really won't make much of a difference, right? If you have 1 million observations, whether you divide by 1 million or 900,999,999 something, it's not going to make a huge difference. Yeah, so only in small samples is this a degrees of freedom correction that is really important to take into account. Sigma squared and S squared, we can also look at sigma and S, where sigma refers to the standard deviation and in the population, and S refers to the standard deviation in the sample. And the only difference between sigma and sigma squared is the square. So what is sigma squared then? It is the square root of, what is sigma? It is the square root of sigma squared, and that's the population standard deviation. And the same thing for S, it is the square root of S squared, the sample standard deviation. Why square root? Well, that's the reverse of taking a square. So if you take a square of a value and you want to get back to the original value, you take the square root. That's basically just doing the reverse. Why would you want to do that? Well, the population variance gives us a dispersion expressed as the average squared distance to the average. This is correct. It's a number we can totally use, but it has one downside. It's on the squared scale of the original variable that we were looking at. So it's on a completely different scale. That's, of course, much larger because it's squared. And of course, it would be nice if we could just express the variability of our variable on the original scale of the variable. So it's actually meaningfully related to the value of the mean. So we can say, well, that's the mean, and this is the variability related to that mean on the same scale. And that's why we have a standard deviation. It's nothing more than the square root of the variance. So we can get rid of having taken the squares to get a positive sum for the square deviation, for the deviation scores. Basically then we are back on the original scale of our variable, which also means that if you need to interpret a standard deviation, then roughly what it means is the average distance to the average, the average deviation score, basically. Or the mean distance to the mean. Can use both of them equivalently. So that's the standard deviation. And because the standard deviation is on the scale of the original variable, it really tells us how wide or small our curve is. So if there's a lot of variability and we get a large standard deviation, then this curve will be very, very wide, this bell-shaped curve. And if we have not so much variability, if all the values are quite close together, then the standard deviation will be small and this curve will be very, very peaky and very, very thin, basically. So going back to our example, these numbers we have seen already. So the individual observations for the grade, the deviation scores, and the square deviation scores, and the sum of all these things. So now we can use these numbers to calculate the variance to see, well, how much variability is there around the mean grade for this random sample of 5 students. Well, did you figure it out? Yeah, well, just follow the formula, right? So the formula for calculating the sample variance in this case, because we're talking about the sample, is, well, add together all the individual observations for our variable x, which in this case is the grade, minus the mean value, take the squares of this difference, so take the square deviation scores, take the sum of those, and divide them by n minus 1, the sample size minus 1. In this case, we already know that the sum of square deviation scores is 23.2. Well, we know that our sample size n is 5, so we know that we have to divide 23.2 by 5 minus 1, which works out to 23.2 divided by 4, which, and you can check with your calculator, works out to 5.8. So the average squared distance to the average grade of 5.4 for this sample is 5.8. That's the variance of grades. Again, would be nicer to express this variation on the original scale. So what do? We calculate the standard deviation. How do we do that? Yes, absolutely correct. Very sharp of you. We take the square root of the variance. In this case, the variance is 5.8. So we take the square root of 5.8, and then we get round about 2.41. So now we know that for our sample of 5 students, the mean value is 5.4, and on average, the students are 2.41 points removed from that mean value in either direction, so either higher or lower. Yeah, so that's intuitively how to interpret the standard deviation. That's nice because it tells us something about the variability that's a little bit more understandable. So that was the most easy part of the prior knowledge. Now let's get into, well, basically the most difficult part, inference, because what we do is inferential statistics. We observe things, but we want to say something about that which we do not observe, which most of the time we refer to as the population, because the population is a concrete thing that we can talk about, that I can give you concrete examples about. But instead of population, you might as well interpret, we use our observations, our sample, to say something about an abstract underlying process that's generating our data that we might not ever be able to observe, the so-called data generating process that I talked about in the first lecture. You can forget this for now. I'm going to focus on drawing in inferences from a given sample from a defined population, so it's a little bit easier for you to follow. But it's good to mention this already. Yeah, so inferences in this case means taking a sample and using that sample to say something about a larger population. So in my 5 PSRM2 exam students are a sample, and maybe I'm a super lazy grader, so once I've graded 5 exams, I don't really want to grade the rest. So I just want to assign some kind of average grade to everybody. So I could say, well, I have these 5 students. I calculated the mean value for these 5 students. I'm just going to use that mean value as a representation for all the students. So in other words, then I'm using the sample mean as a substitute for the population mean. And that's really the challenge. Can we do that? Can we take the sample and calculate whatever we want to calculate as a statistic? In this case, we are keeping it simple. We're talking about just the mean. And can we use that to say something about the mean value in the population? Is that justified? When can we do this? How can we do this? How can we express how uncertain we are when we do that? That's really the basic goal of inferential statistics. And it's a bit of a counterintuitive way of getting there sometimes. So take it step by step. So what we can do is we can use our sample mean to make an inference about our population mean. In general terms, we would call that sample mean an estimate, because it's not the true population value, it's just an estimate of that of that value. Yeah, so it's something that we know is not going to be exactly correct as a reflection of the true population mean. It's just an estimate. And we call it a point estimate when it's a single number. So in this case, the mean can be expressed as a single number. So in that case, that's sometimes referred to as a point estimate because it represents basically a single point, a single number. That's the idea of a point estimate, sometimes also referred to as a statistic. Yeah, and when we talk about the population value that we want to say something about, informally we will refer to this as the population parameter. In this case, the population parameter is the population mean that we're interested in, but those again could be different types of statistics that we're interested in. But for now, we keep it simple. But in general, we can say we can use these estimates based on our samples to make an inference about population parameters that we actually want to say something about, that we actually care about. Yeah. So usually, of course, those won't be known. Usually, you won't have observed the entire population. If it's more about abstract about saying something about an underlying data generating process, you won't ever, by definition, be able to perfectly observe that. So that won't ever be known. But we have our sample mean that we can use as an estimate for our population mean mu. Yeah, and of course the sample mean, because that's something that you observe. So that's known, that is something that you can actually calculate. Cool. So there's a big step we have to make. Using something that we can calculate based on what you observe to say something about that which we cannot observe. That's the goal of inference. And so, of course, the big question is then, well, how reliable is it? I have a sample estimate of a mean value here. I have a mean value of 5.4 on a grade for statistics based on a sample of 5 students. How reliable is it to use this as an estimate for the underlying population mean of grades? That's the big question. And fortunately, we can use mathematics and the application of mathematics to how samples work, how taking a sample works, the so-called sampling theory, and we can make a judgment on that. And that judgment is really based on underlying mathematical proofs. So things that can be mathematically shown to be true, which is nice, which gives us some kind of a secure ground under our feet to at least have a toolbox to say something about this reliability. And a fundamental concept in that, really, really important concept that is incredibly important, that at some point you will internalize the idea of this concept, is the sampling distribution. The idea of a sampling distribution. In this case, we want to say something about the mean value mu in the population. And that means we need to think about the sampling distribution. And what is the sampling distribution? The sampling distribution is basically a thought experiment. And the thought experiment is, what if we would actually have the entire population, be able to observe the entire population, and then draw every possible sample that we could draw from that population for any given sample size? What would happen then if we do that and then would calculate whatever statistic we're interested in all of those potential samples? What would then the distribution of all those different calculated statistics look like? So if we're talking about the mean, we can say the sampling distribution for our population mean mu is the distribution of all values for the average, the sample mean we would get if we would draw all possible samples from a population. Yeah, so let's say there are, I think, 183 students registered in this course at the moment. Let's say that's the population we care about. And let's say I can draw samples of size 5. So I can draw each potential collection of 5 students drawn at random from the entire group of 183 people. And for each of those 5 students, it's a random sample, so that means everybody has a same probability of being included in a specific sample. For each of those samples, I'm going to calculate the sample mean. Then I get lots and lots and lots and lots of different sample means. Some of them will be very, very high because I have happened to get a sample where 5 students score really, really high. Some of them will be super low because I just happen to have stumbled upon a sample where all the students just happen to have scored quite low, right? So I can think about all these different sample means themselves as observations. And what you will see in that case is that, well, if I would take the mean of all those means, yeah, again, the mean of all those mean values. So the mean values for each sample, if I would align them up, put them in a table, and then say, well, this mean plus this mean plus this mean plus this mean until I have all the means and divide by the number of samples, by the number of mean sample means that I've calculated, then that mean of all sample means is by definition going to be identical to the population mean. This is something that can be mathematically proven. So in formal terms, we say that the expected value of the mean, the sample mean, so E stands for expected value, is identical to the population mean. In this case, expected value you can read as being synonymous with mean value. Later in the course, we will talk a little bit more about expected values and their relationship with means. And it's going to be a little bit going deeper, but for now you can just treat them as being synonymous, this expected value and mean value. Yeah, so the expected value of x bar is identical to mu. So that already gives us some knowledge about the relationship between our sample means and the population mean, because we know if we take every potential sample mean and take the average of all those sample means, then we would by definition get the value of the population mean. One way to get an intuitive understanding about why that is true if you think about the most extreme sample sizes that you can think of. One extreme sample size would be that you have everybody in the population included in your sample. So then you would be able to exactly calculate one sample mean, because then you have already everybody included in your sample mean. You get one value for that, so the average of one value is just that value. So in that case, the average, all the sample means, is, of course, identical to the population mean. You can also look at the other extreme. The smallest sample that you can think of is a sample of size 1. So then we would take one single observation in each sample. In our example, one student would be a sample. And then we could take each one of those samples of one observation and calculate the sample mean, which would then just be the value for that observation, because the average of one value is just that value. And then we do that for every potential sample that we can draw from the population of size 1, which is of course identical to just taking all the observations in the sample, adding up their values and dividing by the population size. Yeah, so again there you see that, that's identical by definition. For all the other sample sizes in between, everybody, every observation in the population and one observation at a time, it's going to work out exactly the same way. Yeah, so that's a way of trying to get an intuitive grip on that. Okay, that means we now know something about the central tendency of the sampling distribution. So this thought experiment of what would happen if we would draw every potential sample and calculate our sample mean. We know what the central tendency of that sampling distribution would be. We know that the central tendency would be identical to the population mean. Yeah, which basically means that the most likely value to find would be the population mean. Of course, that doesn't mean that necessarily each sample is going to be a great reflection of the sample mean. We have to also worry about, how far removed are these individual sample means from that population mean, mu on average. So in other words, we want to know also about the dispersion of our sampling distribution. How much variability is there in the individual samples relative to the population mean? Yeah, if there's a lot of dispersion, a lot of variability, then the sample means are unreliable. as a reflection of the population mean. If there isn't a lot of dispersion, then the sample means are more reliable. So we know we somehow have to express this dispersion. And we do that with a statistic called the standard error, indicated again with the same sigma that we used for the standard deviation of the population, but now we add x bar behind to indicate that we are talking about a standard error. And it's no coincidence that the symbol we use for the standard error is almost the same symbol as we use for the standard deviation, because the standard error is a standard deviation. But we use a slightly different symbol and a different term to make sure that we understand what kind of dispersion we are talking about. If we talk about standard deviation, we talk about the dispersion of a variable. A variable, just a characteristic, can take different values, and we want to express, well, how variable are the different values relative to the mean of that variable. The standard error, although you calculate it also by taking a standard deviation, but in this case you calculate it by taking a standard deviation of all the sample means relative to the population mean, mu. So it refers to the dispersion of the sampling distribution of the sample means rather than of the distribution of the underlying variable that we are talking about. So this is an important distinction to make. Standard error refers to the dispersion of the sampling distribution. Standard deviation just refers to this, the dispersion of the variable that we are talking about. So the standard error. It would be nice if we could find a value for that standard error, because then we know how spread out the different sample means would be relative to the population mean. Now, there is a couple of things that we can mathematically prove about the standard error. For one, we can prove that it is related to the population standard deviation. So the standard error and the standard deviation have a relationship between them. And that relationship can be expressed by a simple formula. The standard error equals the population standard deviation divided by the square root of the sample size. So if I take all the samples of size, 5, then the sample size would be 5. So if we would know the population standard deviation and we would divide that by the square root of, in that case, 5, we would have the value for the standard error of the mean. So we would know how far on average our sample means are removed from the population mean. And this is also where you can start to see why having these formulas isn't just helpful to know what you calculate, but sometimes these formulas also tell you something interesting if you think about this. And in this case, if you look at this formula, you see we take the population standard deviation and then we divide by the square root of the sample size. Which means that whatever our population standard deviation is, the larger the sample size is, the larger the number we're going to be dividing it by. So the result of that, the standard error, is going to take a smaller value the larger the sample size is. So the more we increase the sample size, the smaller the value for the standard error is. And on a conceptual level, that makes sense, right? Because, well, the standard error tries to tell us something about how spread out our sampling distribution is. The more spread out it is, the less reliable individual sample means are as an estimate for our true population mean. The larger the sample is, the smaller the standard error becomes, indicating that as our sample increases, our sample estimates become more reliable as reflecting the underlying population mean. So that makes sense. It also means that if you look at this formula, that our standard error can never be larger than the population standard deviation. It's mathematically impossible. At most, it can be equal to the population standard deviation. And as soon as we increase the sample size, it's always going to decrease and be smaller than the population standard deviation. So that's also good to know. As our sample size increases, the dispersion of sample means around our population mean mu decreases. Cool. Now, we can go one step further, because all of that, it's relevant, it's good to know, but we want to find actual numbers and not just woolly language about reliability and certainty and uncertainty. We want to actually find the according numbers that express this uncertainty. And for that, we need to rely on a mathematical theorem, which basically means this is something that is not obvious, but has mathematically been proven to be true. And in this case, the theorem we are relying on is the so-called central limit theorem. Now, don't worry, I'm not actually going to show you the mathematical proofs. I'm not even going to show you the mathematical description of what exactly the central limit theorem says. It's really not necessary for this course that you know, but I'm going to tell you what the implications of the central limit theorem are. And that is, this theorem shows us that the sampling distribution for our mean mu will start to look more and more like the so-called normal distribution the larger our sample size is. So the more we increase our sample size, the more the sampling distribution will take this bell-shaped distribution that we know as the normal distribution. As a matter of fact, the central limit theorem tells us, if we apply it, that this is even true if the original variable, if the distribution of the variable that we are interested in is not normal. Maybe if I'm interested in analyzing how much students like statistics, I might find that the population in the population, that variable is really skewed in its distribution. So for instance, maybe most of the students incredibly hate statistics, and there's just a couple of students that really like statistics. So you say you will see a very skewed, not symmetric distribution, certainly not a normal distribution. And you might say, well, then I can't use the normal distribution. Well, you can't use the normal distribution to describe the variable, but it turns out you can use the normal distribution to describe the sampling distribution for that variable. So even though the original variable may not be normally distributed, the central limit theorem shows us that as long as our sample size is large enough, that all the individual sample means that we could draw from that variable, from that population with that variable, is still going to look like a normal distribution. And how much sample size is needed to use that knowledge? Well, it depends on lots of things, like, for instance, the distribution of your variable. But roughly speaking, this would be the text case rule of thumb. If your sample size is larger than 30 observations, then you will quite quickly see that the sampling distribution is going to look like the normal distribution, which means that we can use the normal distribution to approximate or say something about the sampling distribution for that specific variable. It depends on the underlying distribution of the variable. If the variable itself is already normally distributed, or at least symmetrically distributed, then you can even get away with smaller samples, and the sampling distribution will already look like the normal distribution. But if the variable is super skewed or has in another way a weird shape, then sample size needs to be a bit larger. But so roughly n is 30 is kind of, the textbook rule of thumb, is where you would say this is where the central limit theorem really starts to kick in, basically. Which is great, because the normal distribution, or better, which is actually a family of distributions that all have this kind of bell shape, is a distribution that is actually known, and that can be mathematically described by a formula that is known. This normal distribution is in fact sometimes referred to as the Gaussian distribution, because one of the persons that was really helpful and influential in working out these mathematics behind the normal distribution was Carl Friedrich Gauss. That's the reason why this is sometimes referred to as the Gaussian distribution. But because we know what the distribution looks like exactly, we can also exactly pinpoint how likely different values for the sample mean that we observe are for a given population mean. That's awesome, because now we know that possible values that we could take for our sample mean from possible values will be normally distributed around our population mean mu, and the dispersion of that distribution, so how spread out that normal distribution is, can be described by our population standard error. Cool. this brings us already quite a bit closer, right? Because now at least we have firm ground under our feet and describing the sampling distribution. So for instance, because we know exactly what the normal distribution looks like, we could, for instance, pinpoint where, for instance, 95% of all the observations under that normal distribution would be located. So we can use that knowledge. Because it's a known distribution, we can pick the values within which these 95% of all potential sample means in this case would fall. And we can do that by filling in this formula, taking the population mean, and then that population mean plus 1.96 times the standard error, or that population mean minus 1.96 times the standard error. This will give us two values. And we know that 95% of all our sample means will fall within those two values. Where does the 1.96 come from? It comes from the fact that we use the normal distribution and we know the shape of the normal distribution. And because of that, we can calculate exactly what number would be needed to plug in here. It's actually rounded. It's not exactly 1.96, but for all intents and purposes, we can treat it as 1.96. So in our distribution, we have the mean indicating the population mean indicating the central tendency of the variable. But we can also think about that as indicating the central tendency of our sampling distribution, because we know that the expected value of our sample means is identical to the population mean. But we now know also how spread out, how dispersed this sampling distribution is. So in this case, we would know that 95% of all our sample means would be within that range of mu plus 1.96 times the standard error and mu minus 1.96 times the standard error. So because, then we would have 95% of all our sample means would be in that area. And this, because of course the total number of sample means will be 100%. That means the remaining 5% will not be in that area. And because it's a symmetric distribution, a normal distribution, so both sides look the same, we can just say, well, the remaining 5% will be divided over the right hand part of the curve that's outside of the range and the left hand part of the curve that's outside of the range. So 2.5% of all sample means will be located further to the left in our sampling distribution, and 2.5% of all sample means will be located further to the right. Cool. Okay. Complex stuff, abstract stuff. Let's apply it concretely. So let's say I'm interested in measuring satisfaction with democracy, a variable that you will be working with quite a bit in the assignments. And I want to do this for the Netherlands, also the country for which you will use data in the assignments. And let's say that I know what the population mean is in the Netherlands for satisfaction with democracy. I have asked every person in the Netherlands, how satisfied are you with democracy on a scale from 1 to 10 or 0 to 10, and I calculated the mean value for everybody in the population, and it turns out to be 5.94. And of course, if I have all these individual observations and the population mean, I can also calculate the population standard error, which works out to 0.3. These are completely made up numbers. I don't think they have any kind of realistic bearing to the current situation with satisfaction with democracy, which is, I think, quite a bit higher than that. Yeah, but it's just to have an hypothetical example with actual numbers. So if I know this, then I also know what would happen if I would start drawing all potential samples of a given sample size from people in the Netherlands. Because I would know that the sample means of all possible samples that I could draw, 95% of those sample means would be within the range 5.352 to 6.528. So 95% of all the potential samples would give me a sample mean that's somewhere within that range. Why? Well, we just fill in the formula. The population mean mu is 5.94, and we know that 5.94 minus 1.96 times the standard error, which we know in this case to be 0.3, will give us the lower bound on that 95% within the normal distribution, and 5.94 plus 1.96 times the standard error of 0.3 will give us the upper bound. So we can say, well, 95% of all our sample means will be within that range. And conversely again, 2.5%, only 2.5% of our sample means would actually be smaller than 5.352, and only 2.5% would be larger than 6.528. Yeah, so in other words, it would be quite unlikely to find sample means that are smaller than 5.352 and larger than 6.528. Can happen. We can't exclude the possibility that happens, but it's quite unlikely in this case. Of course, that's all nice and good, but it's a problem because, yeah, well, if we already know the population mean, why go through all this trouble? Then there is no inferential problem. We already know what the population mean actually is. Yes, absolutely correct. But this thought exercise is going to help us if we just have one sample instead of all the possible samples that we could draw from the population. Yeah, because that's the situation we're always going to be in. One sample of all the possible samples that we could draw from the population. Because now we know something about the sampling distribution. And by knowing the sampling distribution, we can say something about how confident are we in our mean sample means by, for instance, creating something called a confidence interval around our sample mean. Because instead of looking at where do 95% of the observations fall around the population mean, we can also look, well, we have a sample mean. What would a 95% confidence interval around that sample mean look like? And it's basically the same formula. Yeah, it's x bar in this case because it's a sample mean, but x bar plus 1.96 times the standard error and minus 1.96 times the standard error, those two values would give you the 95% confidence interval for your sample mean. And that means once we know that confidence interval, we have two numbers that give us an indication of there would be a 95% chance of drawing a sample with the mean x bar when the actual population mean falls within that range. Yeah, it's of course still a little bit cumbersome. Yeah, we're talking actually about the chance of drawing the sample mean when the population mean falls within a certain range. Yeah, so formally we can't speak about it the other way around. What would be the chance of drawing what is actually the chance of drawing this sample mean? What would be the range of sample means if we know the population mean? But we can say, well, there's a 95% chance of drawing a sample mean x bar when the population mean falls within that range around the sample mean. Yeah, so this gives us a little bit more to go on, but still there's some couple of problems we need to solve. And one problem is if we just have a sample, we don't know what the population standard error is. Yeah, if we want to fill in this formula, we need the population standard error. But if we only have a sample, we don't know the population standard error. So that's a problem, of course. What we do know is that the population standard error has a defined relationship with the population standard deviation and the sample size. Now, the sample size is something that we do know. Yeah, we know how large our sample is. So one point of this formula we can already fill in. That's just going to be our sample size. But then we still need, the standard deviation, which we don't observe because we don't observe the entire population. Well, thankfully, we can use the standard deviation based on our sample. So our sample standard deviation, we can use that as an approximation, as an estimate of our population standard deviation. That's cool because that means we can now fill in the formula. We can say, well, if we want to have the standard error, we're just going to take the sample standard deviation and divide it by the square root of the sample size. And this will give us then this standard error of the mean. Yeah, now we're looking at using SE instead of sigma to indicate that this is the sample standard error, not the population standard error. In other words, this is just an estimate of the true population standard error. But at least we can now calculate that. There is a bit of a downside to that, because we're just using an estimate of the standard error and the population standard error, not the actual population standard error, we are introducing a little bit more uncertainty. Yeah, because it might not be always that the standard deviation in the sample is a good approximation. And by implication, it also means that our standard error might not always be a good approximation of the true population standard error. So we need to take into account this added uncertainty, which has as a consequence that the normal distribution is now a little bit too optimistic in expressing how much uncertainty there is, how much variation there is in our sampling distribution. So instead, we use another distribution that looks like the normal distribution, but just flattened out. So if you think about the normal distribution as a bell shape, then just think of that same distribution and what would happen if you would push down on the top and then see the tails come up a little bit. Yeah, just think of it as kind of like a squishy toy. If you push down at the top, then it's going to get wider. Yeah, and that's basically what the t distribution is. It's like a normal distribution, but the tails are fatter. It's wider, so it allows for more variation in our sampling distribution. So that's sometimes called the student's t distribution. And maybe I'll come back later in the course why it's called the student t, on why it's called the student's t distribution if we have time. Yeah. But the good thing about that is, yeah, if your sample is quite small, then it's something you really need to worry about. You can't use the normal distribution. You need to use a t distribution. But there are different t distributions for different sample sizes. And yeah, the larger the sample is, the more the t distribution looks like the normal distribution. And yeah, if you just increase your sample size enough, then it will be almost indistinguishable, the normal distribution and the t distribution. So if you have a large sample, then whether you use the t distribution of the normal distribution isn't going to make a lot of difference anymore. If your samples are smaller, then yes, you need to use this. Then yeah, it's a little bit more important that you use the correct distribution, in this case, the t distribution. But that's great, because also the t distribution is a distribution that we know. So for each sample size, we have a mathematical formula that exactly describes the shape of the t distribution. So all the other steps that we already did with the normal distribution, we can still do. So that means now we have all the ingredients we need to make this inferential step from sample to population. To use our point estimates, such as our sample means to say something about the population parameters, such as the population mean. And we do this formally by testing hypotheses. Yeah, formal statistical hypotheses, which we use to make an inference about the nature of the population based on the sample in a kind of rigid and mathematically grounded way. Now, if we do hypothesis tests statistically, it means whatever hypothesis we have, we always have to split up into two different but related hypotheses formally. Which you hopefully know as the so-called null hypothesis and the alternative hypothesis, indicated as H0, the null hypothesis, and HA, the alternative hypothesis. Yeah. So, just to be clear, we can't prove either of those hypotheses. But what we can do is we can test the null hypothesis, and even though we can't prove it to be true, we can reject it. So we can test a null hypothesis and then look at the data in testing that. And then sometimes the data will tell us that null hypothesis seems very unlikely. So the data that we observe tells us, well, it's very, very unlikely that this null hypothesis is true. And when we can do that, that means we can then take this as evidence in support for our alternative hypothesis. So if we want to test a mean value, we need to start with defining a null hypothesis. And defining a null hypothesis for a mean value means that you have to assign some value to the population mean. Why do we need a null hypothesis? Because we want to work with a sampling distribution. And if we want to work with the sampling distribution, we know how we can describe the dispersion, but we need to locate it somewhere along the original variable. Yeah, so what is the center of that distribution? What is the central value of that distribution? And that is represented by mu, by the population mean. But we need to place it somewhere. Yeah, we need to have somewhere to put our sampling distribution, and that is the function of the null hypothesis, to give us a place to put our sampling distribution. And what that place is, what that value is going to depend on your research question, what you're trying to figure out. But you do that in such a way that it helps you. It helps you in setting it up in such a way that if you are able to reject that null hypothesis, you learn what you need to learn. Yeah. So that's basically why we need this null hypothesis. And then we can basically formulate three types of alternative hypothesis for that null hypothesis. We can either give the hypothesis, the alternative hypothesis that the population mean is actually not of the value that we assign to it under the null hypothesis. So it's just not equal to that value. But we can also get more specific. We can say our alternative hypothesis is that the population mean is smaller than the value that we assign to it under the null hypothesis. Or we can say no, it's actually larger than the value we assign to it under the null hypothesis. Yeah. So these are three types of alternative hypothesis that you may have for the same null hypothesis. Yeah, is not equal to, is smaller to, or smaller than, or is larger than. So of course we somehow want to test our hypothesis. We could use confidence intervals for that, that we already saw. But yeah, confidence intervals have two drawbacks. And one drawback is just that they are very, very hard to interpret. Because it's, you always need to think about, that sampling distribution, all the potential intervals. And people get confused quite easily when we talk about confidence intervals. Which again, that's why we teach statistics courses, so you learn. But, we also want to use something that's interpretable. So the alternative we have for the confidence interval is the p-value. And both of those confidence interval p-value basically express the same underlying concepts. They also have a direct mathematical relationship, so there is no, in that sense, completely unique information contained in either of them. But I think p-values have the benefit that they're easier to interpret. And the second reason is that a confidence interval means that you are tied to one significance level, which I'll talk about in a little bit what that means. But it means that if you use a confidence interval, you have to assign some number, 95%, 99%, something like that, to the confidence interval. That means that you are already tied to a level of significance. Whereas a p-value, it doesn't matter what your level of significance is for the p-value itself. It only matters for how you use the p-value to make a decision. So a p-value in that sense gives you the information in a way that's more flexible and more informative to use. So that's why we work with p-values. P stands for probability value. So it expresses a probability. What is the probability it expresses? Well, very roughly speaking, you could say it is the probability of finding a certain point estimate in our sample if our null hypothesis is in fact true. Yeah, remember, we can only test a null hypothesis, and we can reject that or not reject that. And we want to make that decision based on, well, what is the probability of finding what we find in our sample if the null hypothesis is in fact true? If the probability is quite large, so it's quite probable that you find what you find in your sample. If the null hypothesis is true, you don't have enough evidence to reject your null hypothesis. But if the probability is really, really small to find what you find in your sample, if the null hypothesis is true, then you can say, well, I have enough confidence to reject that null hypothesis and thus find some support for my alternative hypothesis. So, what do you do in your head? What are the steps that you go through when you do a formal hypothesis test? You start out with assuming that your null hypothesis is in fact true. So you give it a value and you start out with assuming that your null hypothesis is true. And then you're going to decide on, okay, what is my so-called significance level, sometimes referred to as your alpha level or just your alpha. And what does that mean, that significance level? It is basically how much risk you want to run as a researcher to reject your null hypothesis while in fact your null hypothesis is actually true. So your significance level alpha represents specifically the probability of rejecting H0 if it is actually true. And if we reject a hypothesis, in this case a null hypothesis, while it is in fact true, it means we make an error. yeah, our judgment is wrong. We are in error in our judgment about the hypothesis. And yeah, there are two types of errors that you can make. And type 1 error and this type 2 error. We'll come back to this later in the course. But for now, hopefully you kind of remember vaguely that if you reject a null hypothesis that is in fact true, you are making a type 1 error. Yeah, type 1 error, I'm rejecting my null hypothesis while I actually shouldn't be rejecting it. Yeah, so if you have done that, you set your significance level somewhere, some value between 0 and 1 because it's probability. Then you can calculate your point estimate, so in this case the mean value. Then you can use that point estimate to calculate your corresponding p-value, your probability value. And then you can say, well, if that probability value is smaller than my significance level alpha, I can reject my null hypothesis. And because I can reject my null hypothesis, my alternative hypothesis will be supported. Yeah, so that's the whole idea behind this calculating a p-value and then comparing it to some significance level. And then if it's small enough, if it's smaller than significance level, then you have what they call a statistically significant finding. Something we'll talk about quite a bit more later in the course. One thing I already want to warn you about is probably already thinking 0.05, 0.05, significance level 0.05. Because you will quite often see that textbooks just treat it as, just set it to 0.05, but also publications, scientific publications, often they will just, assume that the significance level we work with is 0.05 and call every finding significant if the p-value is smaller than 0.05 and not significant if it isn't. Which we should know is equivalent to using a 95% confidence interval. Again, confidence interval p-values are actually the same information, just expressed differently. But what we should also know is that there is nothing special about 0.05. It's really an arbitrary number. There is nothing magic about that. There is no, let's say, hypothetical magical border where that distinguishes significant between insignificant findings. It is just a kind of convention that for many research situations, like a lot of the type of research you would do, can be quite convenient because, it is a reasonable significance level to work with. It is a reasonable risk to run with the type of data that you would typically be using to say, well, the risk I'm willing to run to incorrectly reject my null hypothesis to make a type 1 error, I want to set that at 5%. But it really depends on the research context. So for instance, if you have really, really large data sets, you have a lot of what is called statistical power. So it's very, very easy then to reject a null hypothesis. Then often it can make sense to have a much more conservative, meaning lower valued alpha. So then you might want to set your significance level to 0.01 or even smaller than that. Yeah, so there's nothing magical about that. And ultimately, you need to know what these numbers represent and how they relate to, your data and your models. And ultimately, you need to make a decision as a researcher. The important thing is that you are clear about how you reach that decision and communicate it clearly. Yeah, but that's about significant level. So that's the steps we need to take. Of course, we need to have the p-value. That means we have to somehow calculate that. How do we do that? Well, we need to first calculate our test statistic. And because we now use the t-distribution, we're going to use values on the t-distribution as a test statistic. Yeah, so we can calculate a test statistic that tells us something about where are we in our t-distribution. Unfortunately, the formula for that is relatively simple. So if you want to calculate a t-test statistic for a sample mean, you just take that sample mean and do minus the population mean under the null hypothesis and divide by the sample standard error. Right? So the difference between the sample mean and the mean in the population if H0, if your null hypothesis would in fact be true. Again, we need a null hypothesis because we need a location for our sampling distribution. In this case, our sampling distribution looks like a t-distribution. So basically we scale that to a t-distribution. Yeah, because if you have then that t-value, you can, mathematically check against the t-distribution. if you did previous statistics courses, you probably at some point would have had to look up t-values in a big table with lots of different potential t-values for different t-distributions with different sample sizes and different alpha levels. Um, uh, Fortunately for you, you don't have to do this in this course. You can just let SPSS calculate the t-value for you, but you need to know what's happening there. So you need to know that the p-value is based on, in this case, this t-value. Yeah, so this t-value, if you compare it to the t-distribution, gives you the probability of finding this t-value or a larger t-value if your null hypothesis is in fact true. Yeah, and then you could say, well, you could either look at both sides of the t-distribution, like normal distribution, asymmetrical distribution. You would do that if you have an undirected alternative hypothesis. So if the population mean under the alternative hypothesis could be either larger or smaller than your population mean under the null hypothesis. But you could also formally say that you only look in one tail of the t-distribution if you have a directed alternative hypothesis. So for instance, if your alternative hypothesis is strictly that the population mean is actually smaller than what you have hypothesized on the null hypothesis, or conversely that is larger than that, then you could only look in the right tail of the t-distribution. Now, strictly speaking, this is true. You could do this. And you should know that if you don't tell SPSS otherwise, it will assume that you have an undirected alternative hypothesis. So it will give you a p-value based on a two-sided test using both tails of the distribution. But you could say formally, it is true that if your alternative hypothesis is directed, you could actually divide that p-value by 2 to indicate that you are only looking at the left or only at the right tail of your distribution. And strictly speaking, this is true. However, I would advise against ever doing that in most situations that you would typically encounter. Because this is something that I would only do if, let's say, you have a strong theoretical argument that it really can only be going in one way, that the actual population mean can only be smaller than some value or can only be larger. And that's usually not true for the type of research that we do. So I would advise against that. Also, the standard is just nowadays to use the two-sided probability value unless you have really, really good reason not to do so. So if you don't, then you would have to very, very clearly communicate that, because otherwise people just assume that you're using the two-sided test. Yeah. For this course, you don't need to worry about that. We're just going to use two-sided tests. We're not going to divide anything by 2 or worry about whether the alternative direction is negative or hypothesis negative or positive directed for calculating the p-values. But yeah, that's formally this is true and correct. Okay, so let's close up with applying this again to a concrete example. So let's say I want to find out about mean satisfaction with democracy in the Netherlands. And I don't know, let's say that I have observed that it was quite low in the past. Maybe a couple of years ago, I know it was around 2. So I wonder whether it increased now. So my question might be, is the mean satisfaction with democracy in the Netherlands now higher than 2? Yeah, so that's a somewhat interesting question. And that's a question we can directly test. Why can we directly test it? Well, because now we can specify a null hypothesis and an alternative hypothesis. Because, well, if we want to find out whether mean satisfaction with democracy in the Netherlands is higher than 2, then, hey, we know what the null hypothesis is supposed to be. The null hypothesis is supposed to be that it is 2, right? Because we want to find out whether it's higher. So if we want to find out whether it's higher, then we need to be able to reject the null hypothesis that it is in fact 2 in favor of the alternative hypothesis that it is larger than 2. Yeah. So that's great. In this example, it's pretty straightforward. If you want to find out whether mean satisfaction is larger than 2, well, then you need to test the null hypothesis that it is 2, because if you can reject that null hypothesis and you find that in your sample the mean value is actually higher, then you can find evidence that in fact in the population also the mean of satisfaction of democracy has increased. So hypothetically, these are values that I could find. Again, I completely made them up. They do not in any way reflect real numbers in the Netherlands. But let's say we find the sample mean of 4.33. So okay, great. That's at least the sample mean is higher than the population mean. Yeah, so at least that's in line with the alternative hypothesis that it is in fact higher. But of course, we need to worry about generalizability. We need to worry about the reliability of this sample mean as an estimate for the population mean. So let's assume that we know that we have a sample of 1,000 people, and let's also assume that we can also calculate the standard error, and that works out to 0.22. Well, then we can just do our formal hypothesis test, because then we can calculate the t-value and compare that to the t-distribution. So how do we calculate the t-value? Great, you are still awake, you still pay attention. Yes, the t-value is our sample mean minus mu, the population mean under the null hypothesis, divided by the standard error, which in this case is 4.33 minus 2, the population mean under the null hypothesis, divided by 0.22, which works out to 2.33 divided by 0.22, which is round about 10.59. So now we have the t-value. We can use that t-value to see where are we in the t-distribution, to see how likely is it to find this t-value or larger if the null hypothesis is true. In other words, to find our p-value. In this case, I don't know anymore exactly what it was, but it's something like 0.0000 and a couple of zeros and then something. So way the heck over in the right-hand side of this picture. So if we have located our sampling distribution with the null hypothesis, yeah, so we have given it a place. That was the function of the null hypothesis, to give a place to our hypothetical sampling distribution. So we said, well, we're going to locate it at 2, and then we used our knowledge of what the dispersion of that sampling distribution would look like, because we know, yeah, it follows a t-distribution where the spread is given by the standard error and by the sample size. And then we can find exactly the place where that t-value would be. And it's way over here somewhere, so way outside of our, well, let's assume we work with a significance level of 0.5. It would be way outside of the area that in the area of rejection, as that would be called. Yeah. So in this case, we get a super small p-value, which means that, yeah, smaller than 0.05, we can conclude that we can reject the null hypothesis that the mean value in the population is 2. And that means that we found some support that it is in fact higher. Doesn't mean that it's exactly 2. That's just our sample mean, but at least we found support that it is higher than 2, because it's very unlikely that it is 2, given the mean and the standard error that we find in our data and the sample size that we have. Yeah. So yeah, that's it basically for me for this refresher course. Probably was, yeah, somewhat intense, but I think that's good, because yeah, if you now have found out what you don't know, you can ask me about it this Friday, or study yourself, whatever you prefer. I'm here for you this Friday to answer any question about this. But yeah, make sure that you do get it, because this basic knowledge is going to be fundamental for the rest of the course, because yeah, we're going to make things more complicated, more difficult, but the good thing is it's also going to become a heck of a lot more interesting, and the types of hypotheses that we're going to test are also going to become a lot more interesting than this one. Yeah, but that's it for me for today. I'll be seeing you online. Bye bye.